Okay guys, so I'm going to do a video on 4.1, 2, and 3. They'll be all in their own little video to make finding things easier. I'm just going to do a quick reteach on the basic rules of derivatives in section 4.1. I am going to go in this order with the exception of notation. I do want to talk a little bit about notation to begin with, and then we'll go about talking about the rules. So there's Leibniz notation, the derivative of a function with respect to x. We're always going to take the derivative with respect to x. Sometimes it's a t, sometimes it's a different letter. It depends on the function. But if the function is, a function of y containing x, then we're going to take the derivative with respect to x. The only time you're going to see this difference in variable is when we do related rates, and that's a few sections down the road. I'm having a pumpkin spice coffee. Alright, so a lot of times when we have a function, let's just say y equals 3x plus 2, when we say we want the derivative of that thing, we do y prime, right? Well, there's no difference if I write dy dx, meaning the derivative of the function y with respect to the variable x, because this function y contains x, or if I write, y prime is equal to, and then write down the derivative, those are equivalent. The other way is we can say the derivative with respect to x, meaning we don't have to identify any particular function, okay? So, if I say the derivative with respect to x of some function of x, I can say, well, that's f prime of x. We know that's the derivative. Alright? But, I can always say the derivative of the function, whatever the function may be, so maybe it's this one up here. And I can say that this thing is equal to 3, and we'll talk about why it's equal to 3 in a second. Okay? So just different notations. When we do related rates, we're going to use Leibniz notation a lot, but really AP doesn't matter which one you use. Generally, if they start with dy dx, you'll say dy dx equals, and you'll write down the answer. If they say, y is equal to something, find the derivative of y, then you could write y prime, or you could write dy dx, it wouldn't matter. So you'll refine that and get used to that as we do more and more derivatives, especially once we get through related rates. But for right now, my main concern is that you can just follow the rules and take the derivative, okay? So let's look at the derivative of a constant function first. A constant function, you're going to have to pardon, my dog is going insane. Right, Ella? See, I'm going nuts. A constant function is just a horizontal line. I don't know, y equals -1, y equals 3, something along those lines. And so, I'll use y equals to -1. If this is -1 right here, that's just the horizontal line that goes through the point 0, -1. Okay? No matter what x value I plug in, the height of the function is always the same. It's -1. So the idea is that the derivative of any constant function is 0, because if I draw a tangent line anywhere along this, it's going to be a flat line, a horizontal line, the tangent line would be. And so that means that the tangent line has a slope of 0. So since the slope of the tangent line is 0, we would say that the derivative of this constant function, so if f of x equals to some constant, we'll call it c, then we know that f prime of x is equal to 0. Okay, so that's the constant function rule. If c is a constant, if we take the derivative of a constant, it's 0. So the derivative of y equals -1 is 0. The derivative of y equals to 3, which would be this line up here, same thing, tangent lines would be horizontal or flat, so the derivative of that would be 0. And that's it for the constant multiple rule. Now once again, there were kids in class wanting to take the derivative of a constant multiple and call it 0, and that's wrong. A constant is a term in a polynomial. Okay, so for instance, back up here, this linear function, 3x plus 2, the constant is added, in this case, to that 3x. It's a term in a polynomial. This is one term, that's another term. This is the linear term, and this is the constant term. Okay, so it has to be added or subtracted from the function in some way in order to be considered a constant. And so, in this case, that derivative of that number 2 would be 0. But if you have something like, 3x squared, well, this is a constant multiple. It's being multiplied to that variable. So you could say 3 times the derivative with respect to x of x squared. In other words, you're taking the derivative of the function part, which is 2x, as you now know, and then you're multiplying that 3 back in, so it'd be 6x. Okay, this is not 2 to the x, it's not a base, it's just a number, it's another constant multiple times x. So just keep that in mind, that if it's being multiplied to the function, it doesn't follow this rule because it's a constant multiple. This is just a constant, and that means it's either a constant function or it's a term that's constant in some polynomial. So that's the constant term, that's the linear term, okay? So, these polynomials, just, side note here, I don't know, 4x cubed minus 6x squared plus 3x minus 12 or something. This is the cubic term, this is the quadratic term, this is the linear term, and that's the constant term. Okay, so again, when we take the derivative using the power rule as we went over in class, we'd say, well, f prime is equal to 12x squared minus 12x plus 3. The derivative of that term is 0, right? So anyway, keep it in mind that this is a constant because it's a term, it's being subtracted from this polynomial, whereas it's not being multiplied. These multiples here, those are constant multiples. They don't go away, they don't become 0 because they're multiplied to a variable. So I hope that straightens that out. Alright, a linear function, y equals mx plus b. Okay? The derivative of a linear function is the same as the slope of the linear function. Okay? So f prime of x, or you could call this y prime since I wrote y equals, is equal to m. That's the linear function rule. So that's why this little function up here, 3x plus 2, that's a linear function. That's of the form mx plus b. That's why the slope would be 3, because the slope of this function is the derivative. I don't know, here's another example. So 6x plus 4, y equals. So y prime would just be 6. It's the slope of the linear function. That's your derivative. Capiche? And by the way, linear functions do not look like this. They're not flat, right? This is the line y equals x. Right? And then, so the y-intercept 0 and the slope is 1. If I change the slope or the y-intercept, then this line could move up or down or reflect, or a whole bunch of different things could happen. So it has to be of this form, y equals to mxb plus b, or the function must just have x to the first power, and that's going to represent your linear function. And it'll always be the slope of the linear function itself. Here's another cute example of a linear function. My paper. Y equals pi x minus 7. Now, you don't see pi times x. You don't see a linear function that looks like this very often. But what's the derivative? The slope here is pi, right? 3.14, so the derivative is pi. Alright, then finally what we did was the power rule. Power rule. The power rule says that if you have a function or a variable raised to the power of n, where n is a number, 2, 3, 4, whatever, then, so if this is y equals x to the n, then the derivative is equal to n times x to the n minus 1. In other words, I'm taking this exponent and I'm multiplying it to the front. Okay, so my coefficient's 1 here, so it's n times x, and then I subtract 1 from the exponent. So if y is equal to x to the 5th, and I know that y prime is equal to 5x to the 5 minus 1 is 4. Okay, if y equals x, I don't know, to the 121st, then y prime is going to be equal to 121x to the 120. And if you look at my proof of the quotient rule, which I used the limit definition, so I just made a video like, I don't know, 20 minutes ago or something. You can find all of these derivatives using the limit definition of the derivative. So just keep that in mind if you want to have some fun. They're in the book, but you know, if you're in the mood to think about something like that, you can do that. Alright, so for polynomial functions or functions where we have x to the n, we're going to use the power rule. Now a lot of times we don't just have a coefficient of 1. We might have something like y equals to, I don't know, 7x cubed minus 4x squared plus 2x minus 3 or something. So I'm just making these up. And the idea is you take, when you have a polynomial, you take the derivative term by term. So y prime. Now again, I'm taking the 3 and bringing it down, but I have to multiply it to the 7, so it'd be 21x squared, negative 8x. The derivative of x is 1, okay, so just 2, and the derivative of 3 is 0. So the derivative of that cubic function is a quadratic. Okay, so then we started looking at strange exponents. So something of the form y equals 2x to the 1/4 minus 3x to the 2/3 plus 6x to the 7/2 plus 2. Again, I'm just making these up. And we're going to do the derivative the same exact way. We're going to bring this power down, although it's fractional. We're going to cancel it out if we can. If we've got a, you know, coefficient that divides in evenly somehow, we're going to reduce that down if we can. If not, we leave it alone. And we're going to subtract 1 from the exponent. So for the first term, it's 1/4 times 2x, and 1/4 minus 1 is negative 3/4. So if I just clean that piece up, 2 goes into itself once, it goes into 4 twice, so I've got 1/2 x to the negative 3/4, and you leave it like that. For the next term, I've got a minus, so I'm going to bring that down. I've got 3 times 2/3, which is 2. X to the 2/3 minus 1 is negative 1/3. Here I'm going to bring the 7/2 down times 6. Well, 7/2 times 6 is 21. So it's plus 21. X to the minus 1, I've got negative 2 plus 7 is 5/2. And the derivative of 2 is 0. So that would be the derivative right there. So these you're going to practice a little bit because now you're adding, subtracting fractions. But otherwise, most of you guys are doing pretty good with it. And if you need some, you know, extra examples, just let me know. Also, now that we're doing the rules of derivatives, remember that position is usually s of t or x of t. Position function. Okay? The derivative of position is equal to velocity. The second derivative of position is equal to the first derivative of velocity, which is equal to acceleration. So when we start doing applications, now we're going to start dealing with acceleration and velocity a little bit more. Alright, and I'm just kind of browsing through the book here to make sure I'm not leaving out any little tidbits about this, but that wraps up section 4.1. So I'm going to stop and go to 4.2.